So, hello, I'm Ettore. I'm a student of a school which was founded by Elon Musk, and I like Rocketry. And today I'm going to interview their group, which stands for Delft Aerospace Rocket Engineering. And they're working on a cryogenic called liquid-fueled rocket engine. I'm happy you're here. Can you introduce yourselves a bit?
My name is Nathaniel. I am the team manager of Project Sparrow, which is one of the projects up there. Currently, we're the flagship project, meaning that we have the most members, and we also have some full-time members, such as myself. That means that I work in Project Sparrow about 40 hours a week, so I kind of really stopped my studies after the second year. Normally speaking, I do aerospace engineering. But yeah, I stopped my studies to work on this for a year with this team of amazing people, and I'm having a lot of fun so far. I guess about me, in my free time, I like to play some baseball, do some jogging, play some music sometimes, though quite poorly, but I enjoy it.
Yeah, so my name is Karman. I am an aerospace student at TUDelft. I am currently the systems engineer of Project Sparrow. So I'm also a full-time member of the team. So I've stopped my studies to work on Project Sparrow. And I'm originally from Spain, although I've also lived in Italy. And I've been in the Netherlands now for about 3.5 years. I still do not know how to speak Dutch, but I'm getting there. And yeah, in my free time, I like to play basketball and then just do some sports as well.
Do you have any questions for me?
Ooh, actually, if I may ask a question, so you mentioned that you're part of Elon Musk's school, or the school that he founded. Yes. What does that look like? Is that like your main school that you go to, or?
So practically, Elon Musk founded a school called Astra. Then Elon Musk kind of left from the school, and it became Astronova. I do Astronova. I'm not a full-time student. I do about 5 hours a week, and so it's like my second school.
Okay, and what kind of things do you guys do there?
There are some classes you can choose. I am doing, for example, terraforming.
Think about terraforming, for example, on Mars. Is it a viable option?
Yes, there are some challenges like radiation or lack of nitrogen, but it's not that impossible. It is very hard, but not impossible.
So what are your plans for your studies for university? Like in which year are you in, and like when would you plan to join university?
So I'm in 6th grade here in my local school. For university, I kind of don't know because there aren't any universities nearby which teach something related to rocketry, really. There's some that teach physics, but not that much.
Yeah, I had the same problem where I was from in Hungary. There wasn't really in the whole country any opportunities to study rocketry, so that happens quite often. But yeah, was very lucky to make it to TU Delft because it's a really nice place for people who are interested in that. Yeah, I guess I wanted to ask how did you get involved with rocketry? How did you get interested in it?
So I'm interested in rocketry from a very long time, such a long time that I don't remember when I started being interested in rocketry. I build small rockets. Last year, I built the sugar rockets with rocket candy. And this year, I am building engines with ethanol, so liquid-fueled engines. I don't have access to oxygen, so I'm using an air compressor, which slightly decreases performance. But yes, I've got a plastic engine I'm testing.
Liquid oxygen is not easy to get a hold of, and it's also quite dangerous. So we have to be very careful with that as well. Yeah. So you say plastic engine, is that 3D printed plastic?
Yes, I have a 3D printer, PLA. There's a slight problem that ethanol with air burns at over 1000 degrees Celsius and PLA melts at 190. So but for some reason, they don't melt the engines. They can be I can use them for a couple of seconds, but they don't melt.
Because it also depends on the thermal conductivity of the material, and I mean, I guess the air kind of also cools it around it. Yeah, well, it's kind of a similar problem that we have, honestly. I mean, our engine operates at 3,200 Kelvin, and there's just no material, especially 3D printable materials in metal that can take that. So it's kind of a similar problem to yours. How do you keep it firing?
If I remember correctly, carbon melts at a higher temperature. So if you could theoretically make your nozzle out of graphite, it shouldn't melt. But then there would be the problem of the graphite burning.
Yeah, exactly. Sorry.
Yeah, so we're gonna say the same. Yeah, like the nozzle of our prototype version is graphite, but it can only hold 2 seconds. So we need the other options.
Yeah, and you can't 3D print graphite, so it's you can't really get the complex geometry that we need. But yeah, no, you hit it right on with the graphite. That's an option that you do have.
You had an image with a very big rocket, and there's a big bear. Is that your mascot?
Karman, I don't know. Do you know the backstory of the Dare Bear?
I think it became sort of the mascot of Stratos and of the Dare board. So there is a society of students, and we have a board. So it's a group of members that every year kind of run the society. So we have the president of the board, the secretary, different roles. And I think a few years ago, the bears became their little mascot, and then they took it around to all the tests. So yeah, there you can see the Stratos rocket with the Stratos team, and they brought their mascot.
How many are you, and how do you want to go to space?
It's a pretty complicated question, but I mean, the first part is fairly easy. Currently, we're with 35 students, meaning that we have 9 full-time members, so people really stop their studies, as we said. And then we have some part-time members who do this next to their studies, which is about 26 then. So we're in different departments, such as propulsion, structures, and control and electronics, and turbo machinery. And then there's 3 people currently doing management, which is me and Karman and Philip, who is our chief engineer. In terms of going to space, I guess we started Project Sparrow to build a technology demonstrator, right? So our mission statement is to build a technology demonstrator for a liquid rocket engine that could one day go to orbit. So that's really the goal of the project. It's not necessarily to go to space ourselves, but it is to make a rocket engine that can help the society of Dare, also build a lot of knowledge within this society, where a team, a few years in the future, might actually be able to use that rocket engine and that knowledge and the people that we've taught how to build rocket engines to actually get a rocket to space.
How's your university and how do you study?
I can talk about it, I guess, because I'm an international student. So I guess many people watching this video will also be international students. So the Bachelor of Aerospace Engineering is fully in English. Basically, I can say you can live in the Netherlands speaking English. There is no need for Dutch, although it would be nice to learn it to integrate a bit more with the culture. But the faculty it's highly international. Most of the bachelor is quite theoretical. There is also some practical courses, but what Dare has tried to fulfill is that need for practical experience along your studies. So I think it's a very good addition if you're doing any study at TUDelft to join one of the student teams. And for space, obviously, to join there. If you're looking more into job opportunities with a Bachelor in Aerospace Engineering from TUDelft, I think you have a lot of job opportunities. I know of people that get a job directly after their bachelor's. Many people continue to do their master's. and they usually get lots of internships and jobs even before graduating. So I would think it's a pretty rich study in that sense. And yeah, for the rest, I think Delft is a pretty it's a student city. It has a majority of students. There are lots of student societies, lots of extracurricular activities, not just student teams that do projects like engineering projects, but also there's a really big sports center, and there is there are lots of societies for basically anything that you want to do, from music to more social life to sports.
I guess for myself, I kind of have a similar experience. Delft is like a really fun city to live, but it's also super nice to be surrounded by people who are also engineers and interested in, you know, making the world a better place, especially in aerospace engineering. I kind of, for the first time, I got to meet other people who were also interested in space as much as I am, which was really new to me and quite crazy, because in high school, I mean, it's pretty rare to, of course, meet other people like that. So that's been really fun. And it also means that you really build a network, especially if you're in DARE. You get to know so many really, really smart people who can really help you along on your studies. Not just in like getting grades, but just becoming a better engineer, teaching you kind of that mentorship, I think is really alive in there, which is nice. And it also creates a network of companies that you get to know. Yeah, you get in contact with them, you get to know what they're all about, and they're usually more than happy to tell you a bit about themselves and, you know, recruitment opportunities that they have. So yeah, getting a job from here is fairly easy if you want to stay with an engine.
So your goals for short and long term?
Starts again with our mission statement, which is to build a technology demonstrator. So what that really entails is that DARE has never worked with liquid rocket engines before, and not many student teams have. So there's really a gap of knowledge that we're trying to fill. We're trying to gather data on what our engine might look like, so that data can then later be used by the society to put this engine on a rocket, to design the rocket around it. So I guess that's kind of the long-term goal of the project itself. I guess in terms of short-term goals, we have spent a large amount of this year so far, so since September that we've been working on this, improving the engine, making a lot of improvements based on the first year that we had, because this is the second year of the team. Yeah, we saw a lot of things that could go better. And we've hopefully made some good improvements on that, also from an organizational standpoint, but also from a technical standpoint. And we're trying to test those now. We finally come to the place where we can see if those actually work as well as we thought they would.
How much do you build your rockets yourself?
Yeah, if I can take that one, I think as much as we can. That's the easy answer. I think we have a lot of facilities at the university for manufacturing and production, and we try as much as possible, because obviously it's also the cheaper way, to make things ourselves. But that also allows us to learn a lot about manufacturing techniques, about tolerances, about assembly. There are, of course, some things that we cannot manufacture ourselves. For example, Firebolt is 3D printed in Inconel, and we do not have access to a 3D printer. So we have sponsors that manufacture for us the most critical components or the most tricky components with methods that we just don't have access to. So yeah, the answer is as much as possible for our own learning experience. And the rest, we usually have partners that do it for us.
But that doesn't mean that we're not involved in those. We, of course, designed those ourselves. And we also learn a lot from, as Karman said, the tolerances that have to be used. And, well, I think it's very rare that an engineering project can make everything themselves in-house. Even if you look at something like NASA, the amount of suppliers that they have and partners in the industry, because, yeah, the more complex a system grows, the harder it is to produce everything yourself. But yeah, we're involved in all of the parts. And
if somebody wants to join your team, how can he join?
Right now, we're actually in our recruitment period for next year for full-timers. So each year we try to get a number of people on board who will join the team full-time next year. And that started about a month ago. And what that means is that we give a lot of information. We have a lot of events where people can come and see our system and talk to us and see what it's like to be a full-timer, because, you know, it's of course a big commitment. You're stopping your studies for a year and you're working on this 40 hours a week. So you really have to find it fun. Otherwise, it's not really going to go well. So yeah, then people get to talk to us, kind of see what it's like, what kind of systems they'll be working on, what kind of people they'll be working with. They can ask lots of questions, of course. And then they can decide to apply, which means that they send in their CV, a motivation letter usually. And then most people, we ask for an interview because we want to get to know them better. And because we've been doing this for a while, we know what kind of people would be good for full-time and for different positions within the team. So then we try to see, does this person fit? So we usually talk quite a bit with the person. The interview is usually around an hour even, meaning we really get to know them and see if they're a good fit for the team. Yeah, but normally a lot of people apply from all over, really. It is important that they're from our university, for example, because they need access to the buildings, of course, so they can actually work inside. But yeah, they can live in the area. It's not necessary that they live exactly in Delft. Yeah, I guess in terms of the interview, what kind of questions we give, we have a few technical questions usually, because we want to see what people think like, right? We want to see yeah, what their kind of thinking is. Are they more analytical, or yeah, are they more creative? So there's really lots of different types of thinking and lots of different types of answers that can get very exciting to our questions. So one example of that, for example, would be the fact that, of course, our engine gets very hot, and we ask people who don't necessarily know how we cool our engine. How would you cool an engine, right? How would you cool a rocket engine that gets so hot and prevent it from melting? And then people really get to brainstorm a bit, and they give some pretty interesting answers usually.
Yeah, and if I can add, I guess a question that we get a lot is what do I need to know to be able to join? Like, which courses do I need to take, or what experience are you looking for? And the answer that we always give, and it's the truth, is like, you don't need any experience to join us, because the reason why you join Project Sparrow is to get experience, and we don't expect people to have experience in building rockets at like university level. Like, that would be shooting ourselves in the foot pretty much. So we just look for people that are motivated, that really want to bring this project forward, that really want to contribute. And if they don't know anything about rocket engines, that's totally fine. They will learn it. If they don't know anything about organization, about how to produce a part, it's fine. Like, you will learn it on the job. So what we look for is motivation mostly, and be able to work in a team. It's quite important. So as Nathaniel explained, we have a full-time team. That is the team that basically makes the core decisions, that brings the project forward. But then we also have lots of part-time members that are students that participate in the project without stopping their studies. So they contribute while they're still studying. And yeah, it's important that in such a big team that you know how to work with other people. So those are things that we also look for.
What can you learn by working in your team?
What can't you learn, really? No, in terms of engineering, lots, because it kind of simulates what working for a real company or in a real engineering project is like. And I've heard from a lot of team members this year that they've learned more in the first 2-3 months of the project than they ever have in their life, pretty much. And my experience is the same, because you're suddenly in charge of a whole rocket engine, and that really hasn't happened to any of us in our life before, obviously. So what that means is, yeah, there's suddenly this big responsibility. There's all these tasks that you hadn't even thought of. So you start to learn how to organize yourself and organize work with others very quickly. You also start to learn, obviously, if you're especially in a technical job, you start to learn 3D modeling, and programming very well in ways that you maybe hadn't in university before, different languages or different tasks. You start to learn how to work in a team very well, how to be, really open to each other, help each other, because it can be fairly stressful at times, of course. So yeah, how to support each other. So a lot of skills that, in my opinion, are very, very important also later on. If you want to be a rocket engineer, you can learn in this team. I don't know, Karman, what have you learned so far, you feel?
Yeah, I think mostly on top of the technical aspect, because if you're purely interested in something technical, well, you have the resources to go and learn and do it, let's say. But I think that the majority of the things that you learn are non-technical. They're about cooperation, about organization of a big team. They're about planning, for example. How do you plan for a test campaign? Or they're about logistics, like what do I need to bring? Who needs to be where when? So there are lots of things that you never learned at university in courses, because courses teach you about aerodynamics, they teach you about structures, materials, but they don't teach you about how do you actually get it done. And that skill, in a way, or that like knowledge that you earn, it's really hard to teach. It's something that you need to be there, you need to try it out, and you need to fail at it to be able to learn. So for instance, we organize a test campaign and you bring everything and you forget a pen to write notes. It's really stupid, but it happens to everyone. But then after you forget it once, you don't forget it again. And those small details that you never thought of, they actually build up and they create this awareness in you of like, okay, I need to get this done. And in order to do that, I need to do this, do that, do this, prepare this. I need to ask this person to do this for me. And like that awareness, I think, is something that you don't learn anywhere else.
Yeah. And I think you also learn to work in really tough circumstances sometimes, because, when you're doing an exam on aerodynamics, you're in a nice comfy hall and you have your pen and pencil and whatever, and you can write. And then suddenly we were out a few weeks ago testing and it started raining like crazy. And the wind was blowing and blowing our tents away. And suddenly we couldn't take notes because our paper was getting so wet. And we had to do all the engineering that we'd learned to do in completely different circumstances, and everything was cold, and it's not great for your mood. So suddenly you're in the real world and in situations that you will actually get in throughout your life, and not just sitting in a lecture hall at the university. And I think that really builds your character as well and gives you a sense of what it is actually like to work as an engineer. So that's been really fun.
Yeah, and problem solving, I would say, as well. Because when you actually need to get things done and you have a time window and you're like, okay, we can test on this day, and then you forgot something or something breaks, like the test campaign that Nathaniel was mentioning, so many things broke or so many things went wrong, and you need to solve it, otherwise you cannot test. So that kind of puts you in the situation of like, okay, well, you need to be really resourceful. And I think that's something really valuable to learn.
How do you organize your team?
I already briefly introduced our departments. So there's 3 people in management, and we have 2 people, or now 3 actually, who help with external relations, so public relations, financial matters, and a partnership manager. And then we have our main engineering departments, so propulsion, who are responsible for the combustion chamber of the engine, the feed system that supplies the fuel and oxidizer to it. We have the structures department, which is really responsible for all the ground equipment that keeps the whole system together, like a thrust bench that keeps the engine attached and measures how much thrust we're producing. The tanks that hold our propellants, the tank cages that they sit in, and all the measurements connected to that. And then we have control and electronics, who do all of our measurements. They operate our Rio, which is basically like a flight computer, but for the ground testing. So that actually tells all the valves that are in our system what to do. It also logs all of our data, so we can actually get something out of our tests. And they also write a lot of the software code. So one thing about our engine is that it is thrust vector controlled, or is going to be thrust vector controlled, which means that we can actually move the engine, pivot it, so we can guide the rocket while it is flying. Well, the programming for that, the models that you have to make, and all the coding is also done by Control and Electronics. And then there's the turbo machinery team, which is new for this year. You might have heard of turbo pumps before, which are really important, especially when you go to higher altitudes for rockets. So far, our system has been pressure fed, but we want to move to a turbo pump system, which is not something we have done before, or I don't know if any other student teams have done it before, like at that altitude, but it is very, very tough. So we have a complete department who are just researching and building a prototype for a turbo pump for our engine. So that's how we're organized currently.
Do you have some remote members, and if you do, how can they work in the team?
So I think it's tricky because I think for a while everyone has been a remote member over the past few years because of Corona. So I do think the entire team has moved to a more online environment. Some aspects of it will remain probably forever since they've shown to be quite efficient, and maybe other aspects will move, and we are moving back to in person. As of for every day-to-day communication, we have a Slack server which belongs to the society, and Slack is basically an app for, let's say, communication and documentation sharing, let's say. So it's basically a WhatsApp, but to a company level. So you can also create internal channels. You can organize yourself into teams, and you can have a secure communication as well. So that is the day-to-day of the society. In Sparrow, we usually, when we have to do online work sessions, we work on Discord, or we do Zoom meetings if we have to do, for example, with externals or something a bit more official. We also have labs, obviously, at the faculty, so in-person work happens at the faculty itself. For remote members, I would say we don't usually accept fully remote people. Usually members of Sparrow and there are students at TUDelft. So nobody is fully remote during their entire time. Obviously, if you need to go back home for your family or you're on holidays, then we have the online tools. But yeah, in terms of other tools that we use, we usually use Miro a lot. Miro is a shared online whiteboard, if I can describe it somehow, where basically with your entire team you can work on the same online environment and then draw diagrams, for example, or sometimes we do the planning. Am I missing some other tools that we use? I think those are the main ones.
Yeah, I guess we work a lot in Notion as well with as
a
sort of wiki/library. And a lot of the departments use Agile management, so sprints. So that's how we organize our workflow a bit.
Yeah, exactly. So departments on their own organize themselves in Agile. And then our Notion server is really important. It's basically our documentation center where we have every workflow split, when we can organize ourselves in a really visual way as well. So organize all the documents.
Where do you test and launch your rockets?
I mean, that's obviously one of the toughest parts of our job, is to find a space where you can safely, securely test rockets, because of course safety is the number one priority of us. There's no way we could do or we would want to launch rockets if it wasn't safely, and that's quite difficult in the Netherlands because it is a small country that's very densely populated, so there's not a lot of open spaces where you can just fire rockets or engines. So usually we get some help from people such as the Dutch military. They have a few sites in the country where they also test some of their equipment, and they allow us to test there from time to time. There's no really any other places where you're allowed to launch rockets of the size that we have, of course. There are a few model rocket societies, and small rockets are, of course, you can fire them from some fields sometimes, but we usually have quite a bit bigger rockets where that's not a possibility. And then sometimes we even have rockets the size of Stratos, for example, the Stratos project, that we cannot launch anywhere in this country at all, and we have to go to other places, such as in Spain, where we actually have a larger safety range, and we are able to launch those rockets. So the amount of free area you need around that, again, kind of really depends on the rocket itself, but also on the weather conditions. So if, for example, if there's a strong wind, then you're not sure how much the rocket might be blown off course. So you have to have an extra large safety area, safety range. It's also one of the reasons why we want to integrate thrust vector control into our rockets, because by actively controlling it, we are actually able to keep a smaller safety range where it is safe to be. In terms of weather, the Netherlands is not fun. It's not great for rocket launches because it is very, very rainy a lot of the time. But we've learned to live with that and work with that. As I talked to you about the last test campaign we had, we just work through it and power through it. So there's no other way.
To ask some more technical questions. How do you make your rocket engine? What fuel and oxidizer do you use?
So for the engine itself, most of it is 3D printed in Inconel, and is 3D printed by one of our main sponsors, Materialize. The propellants that we use as fuel, we use ethanol. And as oxidizer, we use liquid oxygen that, as you might know, is cryogenic. So we need to deal with those cryogenic temperatures. And as for these specs, we aim at, we have theoretically a thrust up to around 15 kilonewtons.
How do you design the engine?
How we design it? Well, so the actual combustion chamber itself, we use CATIA, which is a 3D modeling program, and we also use the online version of that, which means that we can actually share our designs between our members. So we first designed it in 3D. Of course, before that, you have a phase where you look at the requirements, like what do you want the rocket engine to do exactly, how much thrust do you want, and then from that, you already have a lot of things that you know about it, like how big does it need to be to produce that thrust? How hot will it get? So what kind of cooling will you need? So it's a whole design process that took, a large part of last year. So quite intense. And then, as I said, we model it in CATIA, and then we send it off to be printed.
Yeah, we also use COMSOL as a simulation model for thermal flows.
And how do you cool down your engine?
So we have two methods of cooling the engine. The first one is regenerative cooling. So basically, the fuel of the engine is used to cool the engine as it runs. So the ethanol, instead of entering the engine through the injector manifold, so let's say the logical way from or the top to the bottom, it will actually go first all the way to the nozzle. It will enter the engine through the nozzle, and there's many channels, really small channels that run along the walls of the chamber, and the ethanol kind of is pushed through those channels back up into the injector, and then injected into the combustion chamber, where it mixes with the LOX. So basically running cool ethanol through the channels, it's one of our methods. The other method is film cooling. So basically at the intersection between the nozzle and the chamber, we have a film cooling ring that injects part of the ethanol into the nozzle. And this ethanol creates a barrier that protects the nozzle from the high temperatures of the combustion.
Do you have any ideas to use cold gas thrusters?
Well, this is part of the rocket design. That is something that we haven't really gotten into yet. So once we have this engine done, we want to either start a new project that maybe builds a rocket around it or continue this project to do that. So it's not something that we ourselves have been actively working on. It seems like we'll definitely need some kind of rotation counterbalancing, because of course the thrust vector control can control our pitch and our yaw, but not our roll. But actually, one of our previous projects, Stratos 4, already had a roll control department that exclusively was just there to look into this, into this issue. Karman, do you have any more info on that?
Yeah, I can give a bit more. So basically, one of the reasons that was was found for the failure of the launch of Stratos 3 was the pitch roll coupling. So basically, coupling of the frequencies, and the method that was found to prevent this was by controlling the roll of the rocket. And for that, a roll control team was formed. And this roll control team of Stratos 4 worked for about 2 years on developing these thrusters. And they've never got into actually testing because the Stratos 4 rocket has never flown. So most likely in the future, if the next Stratos rocket with the Sparrow engine were to fly, and the legacy, let's say, of that roll control team will be also implemented in this new rocket. So it is not something we're working on currently, but it is most likely something that the next team that designs the rocket around this engine will have to implement.
Will you use thrust vectoring?
Yes. So as I said, we are developing a thrust vector control system. Currently, it's more of a demonstration to show that we can actually do it. Thrust vector control, of course, is pretty complicated, especially because, when a rocket is actually flying, you need very high, very low latency and very high reaction speeds, of course, of the actuators that move your engine around. So it's a coding challenge. It's also a challenge of getting the right equipment, of course. It's very difficult to get actuators that are precise enough, that are quick enough, and light enough at the same time. But yeah, currently they're developing the simulation models of how we can actually control our engine in real time based on the way that it is moving. So that's definitely in the works, and it is also definitely one of the key things that we said at the beginning, is that we're going to be a regeneratively cooled thrust vector controlled liquid rocket engine, because there is just no way to get our safety range small enough to be able to guide ourselves into orbit, and even right at the beginning of the flight with the instabilities that you get into a rocket, there is just no way to do that for us without incorporating that thrust vector control. So that's something that's been part of our project from the beginning.
How do you design your rocket?
I think, Nathaniel explained before, so we follow always a structured approach, going from a mission to requirements to designing subsystems around those requirements, and then do some validation testing, and then finally testing the rocket at the end. Currently, we are in the engine development phase, not yet rockets. And in the society, we are the team that is working the most on liquid rocket engines. We also have teams that are working on solid engines, which are usually the engines that the smaller rockets of the society use. And Stratos in the past had a hybrid engine as well. So we kind of have experience with the most common types of rocket engines.
Yeah, and if I can add to that, we also do a lot of research, for example, into new types of propellants. So in the past, for solid rocket engines, we've mainly used rocket candy, which is orbital. But we're right now looking into more efficient ways to power our rockets. We're also getting into hybrid engines again after Stratos, and even some more green solutions, let's put it that way, to power rocket engines. So there's really a lot of research in there is centered around propulsion. And we're kind of the flag carrier of that with our liquid rocket engine.
Do you use trapezoid fins? And if yes, why? And if no, why not?
Currently, we as Project Sparrow are only working on the engine, so we cannot really say what we are using or not using because there is no rocket yet. But there are many other teams in there that are developing rockets right now. So if you're interested, we can also maybe have them come here for a small interview as well. For example, the Europe team or something, and they can explain that the actual rocket design. Because currently we're just in the engine, a really cool engine, but the engine phase.
On your website, it seems that the Stratos 4 has trapezoid fins, I think.
I'm not quite sure why they, in the end, went with that design. But what I can tell you is that the simulations were extensive, as they are for all our rockets. Stratos 4 had a specific simulations department that did safety range simulations, aerodynamic simulations, flight path simulations, to look into what the most efficient design is, especially for things like fins that are obviously crucial and a quite fragile part of your rocket. So I'm sure there was a good reason for why they went with it in the end. I wouldn't be able to tell you myself why.
I think they went with the trapezoid fins because they're more aerodynamic. Because like if you have a triangular fin, then it has some thickness, and then when it goes through the air behind, it leaves a bit of low pressure, so that's less aerodynamic. So I think they went with trapezoid fins so that they are more aerodynamic. Instead,
yeah, that's probably it.
Yes, instead for electronics, do you have like a PCB, or do you have another type of board? What do you use?
So I think for flight computers, we usually have PCBs and like custom electronics that are designed by our electronics team, and produced for us. As for the software, currently we use mostly LabVIEW, which is a control software that also has a graphical interface. Although we're also trying to move towards the direction of Python, since Python is one of the most, it is a language that is growing a lot. Also at the faculty, it is the language that you get taught how to program in. So it would make sense if we manage to do everything we can do with that language. And yeah, in terms of sensors right now for our own engine, we mostly are relying right now, or our control department is mostly working on data acquisition. So we gather data in real time, and we are able to see it and to make decisions during testing based on that data.
Oof. Yeah, well, it's quite a lot of facets to it, of course. Right now, as Karman said, the focus is on gathering as much data as possible during the test. So, of course, because it's still a ground system, we still have a direct cable link to our engine through our flight computer, pretty much. So all our valves are directly actuated. We can gather data straight from our engine with thermocouples and pressure sensors. But of course, yeah, at some point we will have to move towards a flight system where we have a flight computer, which means that we will not be able to actuate it through a cable, but we'll have to send commands and have it work on its own. I think last year's team worked on a real-time Linux kernel for that. So we'd have a latency below 10 milliseconds. So we can actually, basically send commands and have our direction of our thrust vector control change every 10 milliseconds, which is quite fast, of course. So that's what they were working on for that. Any further than that, I don't think we've gotten in terms of a flight system. As I said, we've been developing the models that will actually allow the thrust vector control system to will know which way to pivot based on what the rocket is doing and which way it's pointing. But that's also still very much in development.
Do you use air brakes? Or do you have plans to use aerodynamic surfaces to decrease or increase drag?
There is a very, very large team out there that is called the Parachute Research Group, PRG. And they've done a lot of research into different types of recovery systems. So I'm sure they have looked into this, and probably they're willing to explain a bit more of their research. I know they've published so many papers. So yeah, again, we are still in the rocket part, but there's a lot of experience in there on recovery systems.
Exactly. PRG is a very skilled team, and they've already developed a recovery system for a large rocket. I mean, Stratos 4 is over 8 meters, I think, if I'm correct, and they developed a recovery system for that. So the parachute, if it were to come to that, and we were to put firebolts on a rocket for Dare, then they would also definitely be involved in the recovery system there. I'm not quite sure about like specific aerodynamic surfaces. I don't think we have a lot of experience with that in the society, but we've mostly worked with parachutes so far, and it's something we're able to very well test in the wind tunnels that, for example, are available at the university.
Do you like or play Kerbal Space Program?
I've played around a little bit with KSP before. Sadly, my computer is not really strong enough to handle it at the current moment. I probably need to get a new one at some point because I really like to play. Especially the orbital mechanics part is a lot of fun to me. I mean, the launch part as well, but once you get into orbit and you actually get to see how, burning at apogee, burning at perigee actually gets to change your orbit and lining things up. It's really like all of our courses in university, but right in the moment visualized and actually used. So that's always been a lot of fun to me.
Yeah, same. I think I haven't played as much as other students at the faculty. I think it might be like the most played game between our space engineering students. But yeah, definitely, I think it's a game that can mostly spike your curiosity and also help you have a bit of an instinct, as Nathaniel said, mostly on orbital mechanics. But yeah, just keep you motivated, I guess. So it's nice.
What's your payload?
Well, that's a fun one. I think that's one of the nice things that come along with rocketry is, of course, the opportunity to put something into space if we actually get there. Of course, our first goal right now is not yet thinking about that. It's about actually getting there. But one of our aims when we started out this project was to democratize space. And what that means to us is that we want to give access to space for more and more people, especially students in university and even in high school maybe, by basically showing that even as a student you can work on a rocket project that can make it to space, that can get you to space, that can even maybe get small payloads to space, and that you're not necessarily dependent on large companies or governments to do that for you. Of course, we're not in the phase yet where we can say, oh, in a few years, we'll have this satellite that will be launched by us and will be put into orbit. But this is a step on that road, right? It's showing that students can do this. It's building a prototype. It's moving towards a rocket that can actually make it into orbit and carry, well, potentially then a small usable payload, right? Like right in the beginning, it would mostly, we would be happy to get a camera up probably, or I don't know, some small mementos from the team, that kind of thing. But if this knowledge gets extended, then maybe another team will come along in a few years that say, you know, this Sparrow team, what they did is pretty cool, but we can do it better. We can build an even bigger engine and put it on a bigger rocket. And that might be able to transport, you know, a miniature satellite, because satellites are shrinking all the time as well. Everything is being miniaturized. And then maybe one day we can have a project that is exclusively students building the rocket, students launching the rocket, students building the satellite that's on it, students operating it, and I think that would be really, really cool. And I think we're just very proud to be at the beginning of that and to set the first steps in that direction.
Competitions, are they important for your team, and do you have plans to join in some? Have you joined in some?
I would say for Project Sparrow, we are not in any official competition. I guess our competition is ourselves in a way. We do have a team in there that participates in Europe. But for us, I guess what also makes us different is that we don't have a certain place to be by the end of the year. We set the goals ourselves. We can be as ambitious as we want. We can take the direction that we want. And I guess what motivates us is, as Nathaniel said, to just prove that we can do it. To show to the world that if you just motivated, that space is for everyone, that you can get there. What maybe motivates us more in the short term, it could be student records. So I guess for now we are the first student developed, and even I think Dutch developed liquid rocket engine to have fired in Netherlands ever. So that is a crazy record to have, and I think we're quite up there in terms of the technology development, and of course there has held in the past altitude records for student developed rockets, and that we obviously aim to claim again, because we think that this healthy competition between universities it pushes to achieve more. So for us, I guess in terms of competitions is the renown of being the first, or at least of developing something that works and that is complex. And for ourselves, we just want to prove that we can do it and do really, really difficult things in a simplified way.
What do you plan to do in 2022? And do you want to announce something like a new rocket, new sponsors, competitions, or something else?
That's a very interesting question. 2022 is set to be pretty exciting year for us, because we've learned a lot over the past 1.5, almost 2 years of running the project, and we feel like things are coming together, both from a technology and from an organizational standpoint, to where we can actually gather so much more data now than we have in the past, and we're going towards some pretty exciting tests. Namely the first real trial of the 3D printed version of our engine. So last year we successfully hot fired, as Karman mentioned, the prototype. So we call it the battleship version of our engine. But we really want to move on this year towards the actual 3D printed Inconel engine. And seeing that fire after the whole team putting 2 years of work into it would just be such a milestone and a validation of our concept, of course. And then the real work starts. Then we start to gather all the data that we will need to eventually build a rocket around this. There is just an insane amount of data to be gathered, and that's needed to actually be able to validate the design and to make sure that we know everything about it to start designing around that. And then, of course, in September, we will be welcoming a new team who will be taking over from us. We will, of course, well, some of us will stay involved, but in terms of full-time involvement, there will be a new team. So we will be working very hard to pass on that knowledge on, even starting now, with selecting them and having them work alongside us for a while. And then, well, the rest of 2022 is up to them, and we're very excited to see what they will come up with, and push this project even further. In terms of announcements, I don't think we have any big announcements at the moment. We've got some things in the works, so I would definitely recommend you to follow us on Instagram, and for everyone to follow us on Instagram, because that's usually where we make our big announcements. And in terms of partnerships, sponsors, we're always open to collaboration. So that's something to keep in mind if you're a player in the aerospace business.
Are you willing to work for yourself or like some other company?
I think it really depends person to person within there. I think in the past there have been people, well, first of all, Sparrow and we are a student society. We do not plan on making our design commercial. That is a question that we get a lot. We are here to develop something for ourselves in an educational environment. Once we graduate, it has happened before that a group of people from there that have worked on some system before, they graduate and they say, hey, I really like that. I really like working with you. And they go on and they create a startup, for example, with the experience that they acquired. And it has happened before, and it will probably happen again in the future. Because at the end, you're working with someone together for a long time, and then you just like what you're doing and you like the group that you're at. But I would say most people end up getting internships in companies, then getting jobs in those companies or different companies. There's a bit of everything. And I think there's a good support system at the university if you want to start your own company. There's a lot of startup incubators, and a lot of like competitions where you can pitch your ideas and you get financial support. So if you want to start your own company, you definitely have the support for it. And if you want to go ahead and work in another established company, that's definitely also an option. So it's open to everything, I would say.
What are you planning to do, Karman? I'm just curious.
Oh, I think for me, I would first need to get my master's. So I plan on staying at the faculty for now, and then probably joining a company unless something pops up and I really see the opportunity. But for now, I will focus on my master's. You?
Oof. Well, I wouldn't mind working for SpaceX for sure. If anyone's watching. No. Yeah, I think there's a lot of opportunities from the university, as you said. And I also definitely think that I would like to get some experience first within a company, whether that's after my bachelor's or my master's. I'm not 100% decided yet. I would actually be open to start my own startup or with a group of friends from there at some point. But I think same as you, it's nice to get some experience first and get a bit hands-on in the industry, and then see if an opportunity pops up.
What advice can you give to young rocketeers?
Yeah, go for it. Always carefully, I would say. I think rocketry is a field that can be very exciting, but at the same time can also become very dangerous if you don't know what you're doing. So, yeah, I think stay motivated, join the right studies, and pursue it as your career. And in the meantime, if you try to do something practical, just do it safely, under supervision of people that can give you a hand with safety, that can point out to you things that you could be doing wrong, and just being careful. But I think it's a really exciting field.
I guess same for me. Safety is always first. But I guess the advice that I would give is to have as much fun as possible. It sounds kind of, obvious, but I think it's such a serious field that sometimes you get bogged down in the details, and you forget to actually have fun because you're so serious about it and so involved in it. And I guess in addition to that, later on, once you actually start making your decisions about university, think about the why. I think we're at a point now where everyone really has to think about why they're doing what they're doing in life, especially in an industry that can be used for very good things, but also for very bad things. In an industry that is obviously, to begin with, not the cleanest industry. Of course, rocket engines, they consume a lot of fuel. So I think you have to have your heart in the right place, and you have to have your why figured out, because it is a lot of work to get a rocket flying, and a lot of work to get into this field. And if you don't know why you're doing it, or you're doing it for the wrong reasons, then I think that makes it very hard to be successful. Yeah, because that would be my advice. Thanks so much for having us. It was great fun.
Thanks for coming in this interview. It was a nice interview. And thanks for supporting the passion for rocketry.
Thank you.
Thank you.
Have a great evening.
Bye.
Bye.